Faraz Ahmed, a student of MSc Physics second year, and this is PHN 631, and I'm going to present my presentation on the topic Applications of Nuclear Science and Technology. So let's begin. The topics are as follows: Introduction and Discovery, Nuclear Fission, Chain Reaction, Nuclear Fission, Nuclear Reactor. Then I'm going to talk about radiation and healthcare, nuclear medicine in particular, then radiation effects on humans. So let's begin. Introduction. Nuclear technology involves reactions of atomic nuclei, whereas in chemical reaction, usually electrons of the outer orbit take parts in the reaction. Called the valence electrons. But in nuclear science, the atomic nuclei takes part. The applications range from smoke detectors to nuclear reactors, from gun sites to nuclear weapons. Unlike chemical reaction, a nuclear reaction results in a significant change in mass and an associated change of energy, as described by Einstein's equation. Nuclear fissions are accompanied by large changes in energy, which result in detectable change in mass. The change in mass is accompanied by Einstein's famous equation E equals mc squared. Nuclear fission. Nuclear fission is a process by which a heavy nuclide splits into two or more pieces. When a nuclear fission, it splits into several small fragments. These fragments of fission products are about equal to the half of the original mass. 2 or 3 neutrons are also emitted. So one can see a neutron hits a target nucleus, thereby releasing 3 neutrons and 2 fission products in the process. And there's an animation for nuclear fission. So here you can see a neutron hitting a nucleus, fission occurs, 3 neutrons are emitted, and fission fragments are also emitted. Nuclear chain reaction. Chain reaction refers to a process in which neutrons released in a fission produce an additional fission in at least one further nucleus. This nucleus in turn produces neutron, and the process repeats. The process may be controlled, nuclear power, or uncontrolled nuclear weapons. If each neutron releases 2 neutrons, the number of fission doubles each generation. So first there is 1 neutron, then fission occurs, releasing 2 neutrons. These 2 neutrons further fissions, and the process increases. So first there's 1 neutron, then there's 2, 4, 8. So the number of neutrons increases as e to the power n. So there's a chain reaction, and there's an animation for chain reaction. So first there are 2 neutrons, 4 and 8, so on, and this chain reaction. So let's talk about nuclear fusion. Nuclear energy can also be released by fusion of 2 light elements with low atomic number. The power that fuels the sun and the stars is basically nuclear fusion. In a hydrogen bomb, 2 isotopes of hydrogen, deuterium and tritium, are fused to form a nucleus of helium and neutron. This fusion releases 17.6 mega electron volts of energy. Unlike nuclear fission, there is no limit on the amount of nuclear fusion that occurs. So there's 2 isotopes of hydrogen, tritium and deuterium. The fusion occurs, and there's a helium nucleus that's released, and also neutron that's also released. So here's an animation for the nuclear fusion. So there are 2 isotopes of tritium and deuterium, and fusion occurs, thereby releasing helium and neutron. So let's talk about nuclear reactor. We're going into the realm of the applications of nuclear science and technology. So what's a nuclear reactor? Nuclear power is considered as a major component of energy source in the near future. It is an emission-free alternative, which can be seen as a boon, as there is excessive carbon emission. So it's emission-free, thereby creating less pollutants. The pollutants are in the form of nuclear waste, which is harmful, but if we are able to tackle that, then there's one can see a great advantage in nuclear fusion and in nuclear power. The methods of nuclear power. Used in nuclear reactor. The fuel used in nuclear power plant is usually 2 to 3% uranium-235 rich uranium fuel. Plutonium-235 may also be used as a nuclear fuel. Construction and function of nuclear reactor. The main components of nuclear reactor are closed containment structure, reactor control rods, coolant, turbine, pump, and steam generator. Neutrons resulting from chain reactions are permitted only one to pass through, hence the reaction is kept under control. And so this is the typical format used to generate nuclear power, whereas in a weapon of mass destruction, the process is not kept under control, and there is enormous release of energy, and that's leading to destruction of the I mean, it's going to lead a lot of destruction. A lot of heat is produced from nuclear reaction. Therefore, coolant has also an important role to play, because a lot of heat is going to be generated. So uh, uh, we need to control that heat. So a coolant is used, and the coolant helps to extract the heat and maintains the temperature. And here one can see the schematic of the nuclear reactor. This is a rough schematic of the nuclear reactor. So here is the rough schematic. I mean, there's a cooling, water for coolant, and there's this where all the processes occurs. And so I'm going to talk a bit about coolant more. The coolant is usually water, but in some cases, carbon dioxide gas or liquid metal like sodium may be used. The heat produced from the fission reaction is used to heat the water into the steam. The steam is then passed through a steam turbine, rotating it and hence leading to production of electricity. The nuclear reactor is housed in a concrete structure which serves two purposes. Firstly, it prevents the nuclear reactor from damage due to external forces. Secondly, it prevents the radioactive emission from nuclear reactor from escaping into the atmosphere. So we have a thick concrete structure protecting this nuclear reactor, uh, as well as protecting us from the nuclear reactor. And the applications of nuclear technology. Nuclear techniques can be used to diagnose and treat diseases and offer unique ways to assess the efficacy of drugs and detect particularly harmful organisms. Radiotherapy can be used to treat cancer patients across the world. Irradiating seeds with X-rays or gamma rays accelerates the natural genetic mutation processes that can lead to more desirable characteristics such as higher yields, increased protein content, or better drought tolerance. Nuclear and related techniques contribute greatly to improving livestock productivity and food security through improved management of feed resources, reproduction, and diseases. Radiation in healthcare. In nuclear medicine. Nuclear medicine uses radioactive material inside the body to see how the organs or tissues are functioning for diagnosis, or to target and destroy damaged or diseased organ or tissues for treatment. Nuclear medicine can show how organs or tissue are functioning. For more diagnostic procedures, a tracer is injected, swallowed, or inhaled. Then radiologist uses a radiation detector to see how much of the tracer is absorbed or how it reacts in the organs or tissues. Common uses include scans of heart, lungs, kidney, gallbladder, and thyroid. In a type of nuclear medicine called positron emission tomography, PET, usually called PET, the tracer is used to show natural activity of cells, providing more detailed information on how organs are working and if there's damage to the cells. PET scans are often combined with computed tomography, CT scans, or magnetic resonance imaging, MRI, which produces three-dimensional images of organs. Common uses of PET scan include diagnosing heart disease, Alzheimer's disease, and brain disorder, getting detailed information about cancerous tumors to decide treatment options. So here's the video, and then I'm going to play in the next slide. So here's the video of the PET scan. This is basically it's a video explaining how the PET scan works. So here's the video. So let's play it. I mean, I will provide the link in the references. So how do
a PET scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules.
So they have the tracer, which is made of carrier molecules.
The carrier molecule can interact with or bind to specific proteins or
sugars. So it's binding to specific proteins.
The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed.
So FDG is a modified form of glucose using to detect cancers.
A cancerous tumor.
So when it's absorbing a lot of glucose, so I mean there's a hint that there might be a cancer.
The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in the complete annihilation of both particles, releasing two photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
Here's the video. So benefits and risks of nuclear medicine. So if there are benefits, there are going to be some risks, and let's study what are the benefits and risks. Benefits provides information on how organs, tissues, and cells are working. Other common imaging procedures only show structures, where it shows how the organs are and tissues and cells are working. Can be used also in targeted treatments or to kill or damage harmful or cancerous cells, reduce the size of tumors, or reduce pain. Risk: radiation doses are usually higher than in common imaging like X-rays. This means that procedures are slightly more likely to increase possibility you may get cancer in later life. Some nuclear medicine procedures are longer and use more radiation than others. These could cause skin reddening and hair loss. And at last, these are the reference of the various videos that I played on various uh, other sources. I have linked them all, and thank you.